Welcome to another deep dive.
Yeah.
We're tackling operating systems today.
Oh, cool. Operating systems. Those are pretty.
And we've got a classic to guide us, Operating Systems in Three Easy Pieces, by Remzi and Andrea Arpachi-Dusso.
Yeah, that's the one. I mean, it's famous for making a complicated topic, well, kind of fun.
Right. You wouldn't think operating systems and entertaining would go together, but they do here.
Totally. And it's not just surface level either. They get into the nitty-gritty.
Exactly. We're talking resource management, concurrency, how your data actually stays put. It's a lot.
It really is. Like, it's what makes your computer a computer, you know?
Absolutely. And what I love is the authors use this professor and student back and forth.
Yeah. It's way more engaging than just, like, being lectured at.
Right. You feel like you're part of the learning process. So where do we even start? I mean, operating systems seem so fundamental. How far back do we need to go?
Well, the book does something really clever. It starts way back when computers were these huge machines.
Oh, right, like room-sized with the punch cards and everything?
Exactly. They trace how we went from those clunky setups to what we have now. It's fascinating.
It really puts things in perspective, huh?
It totally does. And one of the core things they dig into is processes.
Okay, processes, like multitasking. It feels like that's a big part of what an OS does.
100%. Processes are how your computer juggles all those tasks seemingly at the same time. And to understand that, they get into the proc structure.
Proc structure. Now we're getting technical.
Think of it like a process's ID card, right?
Yeah.
It tells the operating system what the process is doing, what resources it needs, and what state it's in.
Oh, okay, so it's how the OS keeps track of everything that's going on.
Exactly. And that leads us to virtualization. It's how one computer can feel like many, giving each process its own little world.
Right, because imagine if we were still stuck running just one program at a time.
It would be back to the old days of waiting for, like, a printout to finish before you could do anything else.
Talk about inefficient.
Yeah,
The book does a really good job of showing how time-sharing changed the game.
totally. It's like having a chef who can switch between cooking multiple dishes at once instead of making you wait for each course separately.
Now that's an analogy I can get behind.
Yeah.
But all this talk of time-sharing makes me wonder, how does the OS decide which process gets to use the CPU when?
Ah, that's where scheduling comes in.
Schedule.
Yeah. These are algorithms, basically like traffic cops directing the flow of all those processes wanting CPU time.
Okay, so it's keeping things organized.
Exactly. And the book dives into a really famous one called MLFQ, the multi-level feedback queue.
MLFQ. Now that sounds serious.
It's a big deal. Basically, it figures out how to give every process its fair share of CPU time, but also make sure high-priority stuff gets done quickly. It's all about balance, you see.
So it's like that super organized parent who makes sure each kid gets a turn with the toy, but also knows that some kids might need a little more time with certain toys.
Exactly. It's actually such an elegant solution that the guy who came up with it won a Turing Award. That's like the Nobel Prize for computer science.
So we've got these processes, they're zipping around thanks to virtualization, and our MLFQ traffic cop is keeping things smooth.
Smooth operation, yeah. But there's another big player in this whole system, memory.
Right, because all those processes, they need space to actually do their stuff.
And that's where things get really wild, because we're talking virtual memory and paging now.
Okay, I can already feel my brain getting a workout. It's like we're going deeper into the engine room.
Totally. See, with virtual memory, the OS is basically tricking each process into thinking it has way more memory than it really does.
It's like giving everyone a map to a giant mansion, but they're all actually working out of, like, a small office space.
Perfect analogy. And this trickery, that's where paging comes in.
Paging. Lay it on me.
Imagine taking that giant map, right, and dividing it into neat squares. Those are pages. Physical memory gets divided, too, into frames.
Okay, so I'm picturing two grids, one for the virtual stuff, one for the real deal.
Exactly. And the OS keeps a table, like a directory, to track which virtual page goes with which physical frame.
So when a process needs something, the OS is like, hold on, let me check my directory.
And it swaps things in and out of physical memory as needed. It's super dynamic.
Like a very organized librarian, fetching the exact book page you need, even if it means grabbing it from the other room.
Exactly. And the book actually goes through this whole memory trace thing to show it in action.
Memory trace. Is that like retracing your steps after you lose your keys?
Kinda. You're following the trail of a process's memory accesses. You see what it wants, and how the OS uses that page table to translate between the virtual address and the actual physical spot.
So it's like seeing the process check its map, figure out the page, and then our librarian friend hustles to get it.
Exactly. It really helps visualize how this whole system makes limited memory feel way bigger.
It's like magic. But speaking of resources, we got to talk about where things live permanently, the file system.
Ah, yes. Memory is great for the short term, but we need somewhere for data to hang out long term.
Like memory is the whiteboard, but the file system is where we store the important notes.
Perfect way to put it. The file system is like this massive, organized library for your data. The book actually goes through how these systems evolved, comparing older ones like FFS,
FFS, what's that stand for?
fast file system.
That was pretty literal. Was it actually fast?
Well, for its time, yeah. It brought in this hierarchical structure, files and folders, folders and bigger folders like we use today.
Makes sense. Way better than one giant messy pile.
Right. And as we needed to store more stuff, file systems got more complex.
Which brings us to, I'm guessing, the LFS.
You got it. Log-structured file system. That's the big one.
Log structured. So it's like keeping a diary of all the data, adding new entries as we go.
Exactly. It might sound weird, but it's really good for performance, especially when you're saving a lot of data.
So we've gone from giant room-sized computers to time-sharing magicians, and now we're basically data librarians.
I say that.
What's next in the OS world?
Well, now that we don't just have one computer, but whole networks of them, things get even wilder. We got to talk about distributed systems.
Distributed systems. Okay, that sounds kind of intimidating, even for this deep dive.
It's a whole other level.
Yeah.
But the book does a great job starting with the basics, like these things called RPCs.
RPCs, is that how computers gossip with each other over the network?
Basically, yeah, remote procedure calls. It's how you can run code on another machine as if it were right there on your own.
Okay, that sounds incredibly handy in a distributed setup.
Totally. And then there are distributed file systems, too. The book talks about NFS, that's Network File System.
I think I've heard of that one. Isn't that big in, like, office settings?
It is. It's all about sharing files easily between lots of users. Then there's AFS, the Andrew File System.
Okay, another one to add to the list. What's special about AFS?
It's all about speed.
Yay.
AFS uses this aggressive caching, so you often have a copy of what you need right there, even if the real file is somewhere else on the network.
So it's like having a little stash of the most important files always within reach, even if the main library is a bit far away.
Exactly. It's all about adapting to this world where data and computing aren't stuck on just one machine anymore.
It's mind-blowing how we've gone from those early computers that took up whole rooms to this interconnected web of machines.
It really is, and it all relies on these sophisticated operating systems working behind the scenes.
Working hard, keeping things running. But all that intricate stuff we've talked about, the processes, the memory, the files, doesn't mean much if our systems aren't secure, right?
Yeah, absolutely. Security is paramount. And operating systems in 3 easy pieces really drives home that it's got to be built in from the ground up.
Right, it's not an afterthought. It's like, gotta have a good foundation.
Exactly. And one of the key principles they talk about is the principle of least privilege. Remember our bouncer analogy?
Oh yeah, only letting the right processes into the club, keeping things exclusive.
Exactly. But it goes beyond that. You've got access control lists, capabilities, and of course the big one, cryptography.
Cryptography. Now that's where I always feel like I'm entering a spy movie. It's all very hush-hush.
It does have that air of mystery, doesn't it? But at its core, cryptography is just about secret codes, ensuring only the intended recipient can understand the message.
Right, keeping things private.
Exactly. And the book breaks down these different types, like symmetric and asymmetric cryptography.
Okay, now those are some terms I've definitely heard before. But explaining them, that's a different story.
All right, well, imagine you and a friend have a secret handshake. That's kind of like symmetric cryptography. You both use the same key to encrypt and decrypt messages.
So if you don't know the handshake, you're out of luck.
Precisely. Now, asymmetric cryptography, that's a bit different. It's like having 2 keys, one public, one private.
Public and private. I always mix those up.
Think of it like a mailbox, right? Anyone can drop a letter in your public mailbox, but only you have the private key to open it and read what's inside.
Oh, okay. So I can give out my public key, no problem. People can use it to send me stuff, but only I can decrypt it with my private key.
Exactly. And these cryptographic techniques are everywhere in operating systems. They're protecting your online banking, they're securing your emails. It's all happening in the background.
It's kind of wild when you think about how much we rely on these invisible systems to keep our digital lives safe.
It really is. And it highlights that operating systems aren't just about functionality, they're about security too.
It's like operating systems in 3 easy pieces doesn't just give you the technical specs, it makes you think about the bigger picture.
100%. The authors really want you to understand the impact operating systems have on society, the good and the bad.
Because at the end of the day, these are tools made by people for people. And the design choices made have real consequences.
Absolutely. And that's what makes this book so compelling. It's not just a technical manual, it's a launch pad for thinking critically about technology and its role in our lives.
Well said. So for our listeners, if you're looking for a deep dive that will make you appreciate the magic and the importance of operating systems, check out Operating Systems in 3 Easy Pieces.
You won't regret it. It's a fascinating read.
It really is. And on that note, thanks for joining us on this deep dive into the world of operating systems. We'll catch you next time on the Deep Dive.
Until then.